Hi everyone, my name is McCoy Becker. I'll be presenting Probabilistic Fetch, a project focused on combining probabilistic programming components with manipulation-based robotic systems. This is joint work with Arijit Dasgupta, who's in this class, and Nishad Gadaskar, who's not. Why is robotics so much harder than other areas of AI? Every day the internet is seemingly abuzz with the latest development out of OpenAI or Google, massive large language models like GPT-3 combined with generative technologies like DALL-E reaching such a wide non-technical audience. But no matter how many of these large models are produced, one question seemingly remains: where are the smart robots? I believe this short exchange between Leslie Kilbling and Lex Fridman might provide some insight. This is at 37:41 in this interview, but I'll paraphrase. Leslie believes that perception is harder than planning. Leslie goes further. She believes the key problem is representation. One extreme sect of AI enthusiasts follows the bitter lesson by Rich Sutton: general methods that leverage computation and massive amounts of data are the most effective. In robotics and perception, I don't believe that this is true. How do robots perceive objects? This is a scene we could imagine a robot looking at while being tasked with interacting with some of the objects. What does it mean to correctly perceive this scene so that we could plan with that information? One useful piece of information is the posed degrees of freedom of each object in the scene, which deals with their placement with respect to some common frame of reference. There are approaches to pose estimation based in deep learning. Here's dense fusion, a 6-degree object pose estimation model, which is considered state-of-the-art. But we can see this model makes some bewildering mistakes, including placing the bleach bottle intersecting the Cheez-It box in a non-physical way. Another approach utilizes approximate Bayesian computation with a new class of models called probabilistic programs. While this approach is slower than dense fusion for this example, it apparently lacks dense fusion's propensity for non-physical mistakes. In our project, we explored integrating probabilistic programming into a manipulation stack. Probabilistic programming is an emerging AI paradigm which exposes the ability to construct generative models of the world and design custom fast approximate inference algorithms to operate in those models, allowing us to answer queries like, if I saw this thing, what's the probability that thing? Now, I've given you some background in our project. Let's explore exactly what our task is. On the left, I'm showing a static image of our simulation environment. On the right, our task. I'll play it one more time. We throw a pink block across the screen where it comes to rest behind an occluding object. Can we track it with probabilistic programming? Are there unique benefits to applying this approach here? To answer this question, we constructed two modules. The first module is a probabilistic perception module. It consists of a novel combination of modeling and approximate Bayesian inference ingredients. The first ingredient is a rendering likelihood, a function based on geometric reasoning that allows us to compare sample point clouds to ground truth ones in a Bayesian way. The second ingredient is sequential Monte Carlo, an approximate Bayesian inference technique uniquely suited to time series data. We've constructed a generative model using 3D rendering likelihoods and framed object tracking as a Bayesian inference problem. On the top, we're showcasing our generative components, and on the bottom, we're showcasing the results of applying sequential Monte Carlo to our generative model. Our second module is a grass planning module. Approximate Bayesian inference provides us with uncertainty estimates and distributional quantities. Our grass planning module can consume this information and decide what object is likely occluding our target. To effectively perform grass planning on target, this module also contains ransack preprocessing and dbScan clustering, as well as a grass trajectory planner using inverse kinematics. Here are the results when we combine these two modules. We're able to accurately track the object using our generative rendering model as it flies across the screen. We're also able to localize the posterior over the pose of our object of interest behind the occluder. This is directly enabled by the integration of our generative rendering model and our custom approximate Bayesian inference algorithm. To summarize, we've illustrated one potential application of integrating probabilistic programs into a manipulation stack. While our example is quite toy, we believe enhancements to our approach could generalize to more complex scenes and geometries. We also believe our approach is complementary to object detection modules using deep learning, so we don't see these two approaches as being completely at odds. If you're interested in our work, you can interact with us, and we'll publish the source code for our experiments as soon as some of the components are open sourced. Thank you.